Welcome back. This is Thermodynamics 1, Homework 1, problem number 3. Homework 1 is associated with properties, phase diagrams, equations of state, and ideal gas stuff, molecular interactions, but basically chapters 1 and 4 out of Koretsky's textbook. Okay? So then problem number 3 on the first homework is problem number 1.8. 1.8 out of Koretsky. Okay. A second edition. And it says a rigid sealed container. Okay, so we always draw a picture. Always when we can. So we have a rigid sealed container, meaning it's closed up. Okay. And it contains water. Okay. At T equals 100 degrees Celsius. Now if this is water and at T equals 100 degrees Celsius, well, that's kind of where, that's the boiling point at atmospheric pressure. Okay. So that might be significant, I don't know. Let's just keep reading the problem. Some of the water is in the liquid phase. So some of it's in the liquid phase, which means some of it's in the vapor phase. Okay. So if some of it's in the liquid phase, and there's some in the vapor phase, sorry, what did I say? If there's some in the liquid phase and some in the vapor phase, that means I am boiling. And if I am boiling, okay, then, and I'm at 100 degrees Celsius, that means I have to be at 1 atm. Okay. Because at that point, if it's saturated and my temperature set, the pressure is now dependent upon the temperature. Okay. So let's go back to the problem. Some of the water is in the liquid phase and some is vapor phase. Okay. Air is then injected. Okay, so I'm going to bring in air here. Okay, which is typically an ideal gas, all these other things. Okay. In an isothermal process at constant volume. So T initial is also equal to T final. And V total is equal to V total initial and final. Okay, right? Yeah, so, okay. It says, what happens? Okay. Well, let's think about what happens. Okay. And really what we're thinking about is what happens at the molecular level. Okay. All right. So I bring in air. Okay. I keep temperature constant. I keep volume constant. Now, an air is an ideal gas, so let's write down the ideal gas law to see if that helps us. NENRT. Okay, well, this is constant. Obviously, R is constant. Volume total is constant. My moles are increasing. Okay? And so, we probably can say that our pressure is increasing. Okay, when we look at this. And that's probably a good assumption, but, we write down our picture, we write down what we know, and then finally we write down our assumptions. Okay, so assume, the vapor follows this. Assume, that vapor follows, ideal gas, which it doesn't, but we're just going to say that it does. Okay, and that the total pressure is going to change. Okay. But what happens when the total pressure changes? Well, let me rephrase it this way. What happens when the total pressure changes for a saturated system? That's right. For a saturated system, the pressure changes isothermally. Well, I'm no longer two phases. Okay. So unless I can assume that the pressure is constant, which I really doubt it is. Okay. But unless I can, because let's look at our other kind of variables that we've talked about. Okay. Well, the energy. Maybe the energy's changed, who knows, okay? Energy will change, but we haven't really talked about energy, so let's not really talk about energy, okay? The volume, well, the total volume hasn't changed. Has the mass of the water changed? No, it hasn't. So the mass is no different, okay? And the volume is really no different, okay? And so I really have to, there's really nothing in this other than, air coming in that says otherwise with regard to pressure. So we kind of have to assume because there's more moles, I have more pressure. Okay. Now, if I increase the pressure of a saturated system, well, what happens? Well, that's obvious. Higher pressure means liquid. So, all this vapor, all of it, because pressure is dependent upon temperature at saturation, if the temperature stays the same. So what happens is this all goes to the liquid phase. Okay. Now let's think about this kind of at the molecular level. Okay. So I bring in air. Air has particles. Even if it's not an ideal gas, let's think about this. So air comes in, it has things. Okay, so temperature is the same. What does temperature mean? Well, it means the velocities are the same. Okay. And so the velocity of things basically has not changed, okay? So things still are bouncing around more, the same rate, okay? What is different, though, is now I have other things in there, okay? So I'm in a room, I'm running around at a specific velocity, and I'm bouncing off the walls, okay? Now you've put in some, well, I look at my floor, there's things on the floor. There's some bins, there's some cloth, there's some sleeping bags. Okay, as I run, now that they're added in, I'm going to be tripping up on those and having collisions with those. And what does collisions correspond to? That's right, it corresponds to a higher pressure. Okay, because I haven't changed the volume of the system. So, well, I'm tripping over things. Okay, well, I don't want to trip over things, so I kind of collect my buddies, and we become a liquid, basically, is what happens. Because there's just too much crud around here to be running around, so we're just going to hold hands and become a liquid. Yeah. So, bottom line, because the pressure increases, because I've added more moles of stuff, and because saturation pressure is dependent upon the temperature, and I haven't changed the temperature, I have to become a liquid.